Hi, my name is Jonghyuk Park. I will present our paper, Fully Automatic Reflection Remover for 360-degree Images. When we take a photo of reflective material with 360-degree camera, we get a 360-degree image that contains mixed region M with reflection artifact and the reference region R capturing the original reflected scene. With the help of such reference information, we can effectively remove the reflection artifacts from the mixed image region. However, it is challenging to find the mixed region M and the corresponding reference region R. Therefore, previous methods required user interaction to find the region M and R. Hong et al. Requires user-specified mask to find the region M. Han and Sim assume the region M to lie in the center area of the 360-degree image. In contrast, our method does not require any user interaction. We utilize the multi-head self-attention mechanism of transformer, which can automatically capture the relationship between the region M and R. We also devise horizontal window to provide efficient receptive field for the proposed transformer network for finding M and R. Compared to conventional square-shaped window, our proposed window contains both M and R. The proposed method implicitly estimates the regions of M and R by calculating the dot product similarity between the tokens in the proposed method. We designed the encoder and decoder based on the U-shaped hierarchical network using transformer blocks, since the hierarchical structure helps to increase the receptive field of the network. We also applied the Laplacian pyramid to use the multi-scale high-frequency features. For the training of the proposed method, we synthesized 28,000 pairs of 360-degree images with and without reflection. Considering the geometric and photometric relation between M and R, we consider more generalized geometric relations between M and R by randomly trimming away the vertical sides of the M and the corresponding areas of R accordingly. Considering the photometric characteristics of 360-degree images, such as pixel intensity difference between M and R, we synthesize the reflection in the linear image space. Next, we compare the proposed method with the existing reflection removal method to show the qualitative and quantitative performance of the proposed method. The proposed method effectively suppresses the reflection artifacts and clearly reconstructs the transmission images. Also, the proposed method achieves the best quantitative performance and surpasses the existing methods. These are the detailed results of the proposed method. First, we show the region detection performance of the proposed method. Without any annotation or user interaction to specify M and R, our method faithfully removes the reflection in the region M. As shown in the intermediate attention maps, we found that some of the head of the transformer block highlight the mixed region M, while the others focus on the reference region R. Second, we show the reflection removal result in the various scenarios. The proposed method successfully removes the reflection when the mixed region M is at the arbitrary locations. Surprisingly, the proposed method worked on more challenging cases where the mixed region M is separated toward the two ends of the image. Next, we validate the effect of the transformer module in the proposed design. We test 4 cases. Without the self-attention mechanism, using the square-shaped window with the size of 8 by 8 and 16 by 16, and the case of horizontal-shaped window when the height is 2. All the test cases yield low performance, both qualitatively and quantitatively. When we remove the Laplacian pyramids from the proposed method, it fails to remove the high-frequency components of the reflection, remaining the reflection artifacts. This is the quantitative score of the ablation study. The proposed method achieved the best scores. Thank you for listening.